knowing very well that the MOSFET transistor essentially is a four-terminal device. There are different types of junctions formations, including metal semiconductor, metal insulator semiconductor, metal insulator semiconductor, P plus N, P plus N, and so on and so forth. So, and maybe if you are trying to achieve a kind of a very advanced kind of transistors, then you can have heterojunctions, homojunctions, or type of semiconductor p-in junctions. So for this particular MOSFET, which is generally the case, you are having drift and diffusion. So the drift is basically occurring because of the voltage that you're giving essentially to your drain side as well as the gate side. So mostly towards the drain side. So drift is basically coming from the drift, and then the diffusion is actually because of the concentration gradient. Okay, we are talking about N plus P regions and stuff like that. And essentially, what happens is you are having uh, a kind of planar thin layer of inversion happening just beneath the silicon dioxide, which is the insulator surface, and there is a effective electric field. There are two major electric fields that we are talking about, which is why it is called field effect transistor. So the first one is the vertical and the other one is horizontal. So the vertical is basically coming essentially because of the gate voltage, and horizontal is coming because of the inversion layer formation along with the voltage that you give towards the uh, drain side of the MOSFET configuration. So I is equal to QV, where Q is basically just charge density. I think I've done this, but I'm just trying to revise this. So yeah, so basically we're talking about these two fields, the transfers. So transfers longitudinal or vertical, longitudinal, all means the same. Okay, and then you have these onset of inversion when your gate source voltage becomes equal to threshold voltage. So there's a thin layer of formation uh, just beneath the insulator layer, and so basically, so the inversion charge density is proportional to the overdrive voltage, which is VGS minus VT. So Q is equal to W times C of VGS minus VT. I think this you may have done before, but just trying to revise a few things. So we are basically now talking about transistor operation for digital circuits in the three domain, which is the cutoff, um, the saturation, and your linear. So in saturation and cutoff is basically more relevant for us because we are dealing with digital IC design or the VLSI design. Okay, so if you just talk of the MOSFET configuration, as you keep on increasing the drain voltage, there is this sheet of inversion layer that forms closer to the drain part. It starts to pinch off as you keep on increasing the drain voltage, and this basically starts to squeeze down at the drain region, and as you keep on increasing, this will keep moving towards the source region. So the onset of this thinning of your inversion layer closer to the drain region is what you call as the onset of your pinch off phenomena. So basically, We know according to Moore's law, when you had the initial microprocessors, they were 4004 and they were 10 micrometer channel length. Remember, the channel length or gate length is how the industry defines it, and it is the distance. It you can consider. I mean, it's a very harsh or very kind of a general way of defining. It's a difference between the source and drain channel formation. So either you say channel length or you talk about the gate length. So either you talk towards the gate length or the channel length. This is how the industry defines. The important thing here is that that is basically being squeezed down. That is basically being squeezed down over a period of time in a three-dimensional manner. And since it is being squeezed down, you are able to miniaturize the transistor size, and you have come to a stage where from 10 micro 10 micron basically means 10 micrometer channel length or gate length. So some industry call it channel length, the others call it the gate length. So it's squeezed down from 10 micrometer to what you call as 10 nanometers. So there have been continuous motivation to scale down the whole transistor where you have channel length or the gate length as a reference. So when you have a long channel, that is basically if you're talking about the dimension of transistors, say around 0.25 of micrometer and beyond, that is 0.5 micrometer or 1 micron channel length device means transistors. It is gradually it is basically known as the long channel, where your E when your electric field in the x and y direction are not playing much of a role, but as you keep on squeezing down, then the electric field in the x direction becomes equivalent to the electric field in the y direction. So equivalent or probably greater. So this is an important parameter where where you have some of the other important phenomena that arrives and basically uh, plays a havoc to the basic functioning of your transistor. So initially, when it was a long channel, you had the concept of gradual channel approximation, and you had the so-called charge sheet model, and in which the electric field was of the order of 10 power 7 volt per meter. So how do you calculate that? Electric field is 1 volt per 1 micrometer. Okay. So 1 micron and 1 volt, so it becomes 10 power 7, this thing. So uh, basically, the charges, as we have talked, beyond the threshold, beyond the pinch of voltage, this thing starts to, this inversion layer starts to pinch from drain into the source, and then you have a higher concentration here, while there is no direct connection to the drain via the source and the inversion layer. So your so to determine at any point x, the charge density can be defined in this form, and the current basically is defined in this form, right? So at any point X, the charge density is defined in this form, and the current would be defined in this form, where V is basically your drift velocity, which is mu times E, which is also equal to mu times del V by del X, because E is equal to minus delta Vx by dx. Hello, are you still there?
Yes, sir.
Right. I think, yeah. So the extension of this is your ID is equal to WC ox VGS minus VTH minus V of X mu n dVx by dx. So basically, applying the proper boundary condition, that is the potential at 0 is equal to 0, and the potential keeps on increases, and at L, which is the channel length, becomes equal to VDS. We try to determine the by integrating ID x from 0 to L, and that is how you get the overall value of current. So when you solve this, you already know that the value of your ID. Okay, so this is what you get as a constant current throughout the channel would be this value. Please note down. So this is how you make sure that your transistor is actually working as a constant current source. Are you still with me?
Yes, sir.
All right. Have you copied or you
Yes,
already
sir.
know? Okay. So basically, this is your linear region. Below this is the cutoff region, and this is the saturation region. Okay. So this is from here, this point onwards, it is what you are having is the non-linear region, and the current is basically getting saturation. So the peak value of the parabolas can be calculated by simply having a differential with respect to drain source voltage. So del ID by del VDS. So we found that the peak occurs at drain source voltage becoming equal to gate becoming equal to overdrive voltage. So your maximum current ID max is equal to mu on Cox W by 2L VGS minus VT whole square. So here you see it is getting independent of your drain source voltage. Okay. Please note down. So you should be knowing transistor operation in all the three regions, which is cutoff region, saturation region, and the linear region. So in the saturation, it becomes independent of your drain source voltage. So the on resistance, the resistance within your MOSFET transistor for different values of gate source voltage keeps on increasing. So the resistance is inversely proportional to the overall overdrive voltage and is basically given by this expression: R on is equal to 1 upon mu on C of W by L VGS minus VTH, and that you can determine essentially coming from the previous definition of your current. Okay, so how do you determine the on resistance? Basically, when you're talking in terms of the current that is flowing due to the applied voltage, the resistance that incurs when the current is flowing inside your MOSFET while applying your voltage. So as you keep on increasing the gate source voltages, so this is gate 1, this is gate 2, this is gate 3, your on resistance essentially keeps on increasing. Class, are you there?
Yes, sir.
And the transfer characteristics, so we define the inversion in three parts. I think there was a question based on this in your examination itself. And just to elaborate, so the transfer characteristics, one of the important parameters is having the output of current. So basically it is having the current on the log scale on the y-axis and gate source voltage on the x-axis. In the real ideal condition, it should be somewhat like this, but in reality, because of these three conditions, which is the weak inversion, the moderate inversion, and the strong inversion. So again, I will not be going into detail. You get two major or two important parameters, including drain-induced carrier loading and subthreshold swing. And because of the basic physics means the type of material that we are using in the MOSFET transistor being silicon, most probably at room temperature, working at room temperature. So it restricts the so-called subthreshold swing, which can be determined by this graph at 60 millivolts per decade. And that is essentially coming basically because of the physics parameters, or basically laws of physics for that particular material. I think that you must have studied before in your previous classes. So, as we were talking about this, I just would also like to say that most of the times whenever we are talking about transistor operation, we are either talking about the strong inversion or the weak inversion. Okay, so this is a very transient state of moderate inversion. Mostly we are either talking about weak inversion, in which your transistor is supposed to be off and the current is 3 order of magnitude lesser than the current when the inversion phenomena happens and your channel formation underneath the silicon dioxide layer happens. So this delta phi plus, so your strong inversion happens and psi is equal to delta phi plus 2 times delta phi. I think this you can actually understand better once you know how to determine the threshold voltage. So the psi s is essentially your surface potential, and phi f is the difference between the intrinsic level and the Fermi level. So your delta phi is related to phi of t, which is kT by q, and at 300 Kelvin is 26 millivolts. So as I was mentioning, one of the most important parameters that you derive from the log of ID versus VGS graph is the subthreshold slope. So the slope of transfer characteristics determines how well a transistor can be turned off by reducing VGS for digital applications. So the conventional limit of S for MOSFET is 60 millivolts per decade. And S is del VGS upon del of log IDs. Class,
Yes, sir.
have you done subthreshold slope before?
Yes, sir.
You know what I'm talking about? Yes or no?
Yes, sir.
Okay. So the subthreshold slope is defined as the amount of gate voltage required for 1 decade drop in current. Okay. So S is equal to del VGS upon del log of ID, and for silicon based traditional MOSFET transistor has a physical limit of 60 millifold per decade. So this also can be further improved. So those who take the advanced courses on VLSI design, they can talk. Okay, I think is given the basic expression. So, this is the crux. So essentially, the basic equations that needs to be remembered are these: that the current in a MOSFET, once the inversion layer has been formed, has three regions of operation: the cutoff region, where there will be almost no drain current, but definitely there will be a sub-threshold current, which would be three order or more magnitude less than the general one. The second one is the current in the linear region, which is ID is equal to mu n W by L Cox VGS minus VT, which is overdrive, and here there is a role of the drain source voltage too. So as you keep on increasing, it increases with the drain source voltage. So this occurs when your drain source voltage is less than equal to overdrive voltage. When your drain source voltage becomes higher, that is greater than equal to overdrive voltage, which is VGS minus VT, then we reach the saturation region condition. So the drain current is from linear, it becomes quadratic in nature and becomes independent of drain source voltage. As far as the resistance offered within the MOSFET configuration, the so-called on resistance, and its determination is concerned, under the condition that drain source voltage is far lesser than twice the overdrive voltage, the on resistance is inversely proportional to mu n W by L Cox times the overdrive voltage. So the transistor reaches the so-called Deep triode region, when your drain source voltage is less than equal to twice the overdrive voltage. So we have not talked about the process technology. We will talk in half a class or one class in the next class. Important thing is MOS transistor can be used both as a voltage controlled switch as well as voltage variable resistor. So we neglect the linear region in which transistor acts as a resistor, while in saturation it acts as a current source. So for digital application, we will be choosing the off state and the on state as a constant current source. And the steepness of the subthreshold slope decides the speed of transition between the on and off state. So subthreshold swing is a very important parameter which defines the speed of the transistor. Can you see this slide? Huh? Yes or no?
Yes, sir.
Now can you see the slide? Hello?
Yes, sir.
Okay. So now we move further. Now that we have talked about transistor operation for digital application, we now talk what happens when we are forced to kind of not force exactly, but we try to follow Moore's law and continuously push ourselves to achieve that by scaling down a transistor. And as we have mentioned before, that the transistor initially, when it all started, it was very big in dimension. That is why all the things that you see in the past are bulkier, slower, and bigger in dimension. So as time passed, according to Moore's law, they were able to improve upon the transistor in terms of its dimension every 18 or 24 months. Because of this continuous scaling down, the short channel effect, as it reaches a particular dimension, because of the change in the because of the effective increase or shift in the strength of vertical and horizontal electric fields, as well as smaller dimensions, new challenges started to occur in the proper functioning of the transistor. And these effects, due to the scaling down of transistor, are classified as the short channel effects. We shall also talk about the second order effects like the body effects and channel length modulation. So the types of device scaling, the major ones like velocity saturation, drain induced barrier lowering and punch through phenomena. And we shall also discuss about the models which are incorporated in most of these IC design tools and the basic equations to be remembered. So, as we are already talking about the inception of the IC technology and a famous postulate by one of its co-founder. Remember, before this was done by the co-founder of Intel microprocessor or Intel as a company. So before this, Gordon Moore and some of the other co-founders were in the Fairchild, and they kind of shifted and opened up this. So in 1965, one of the co-founders of Intel, Gordon Moore, postulated the number of transistors per unit area, per unit chip area on an integrated circuit would double every 18 or 24 months. And since then, since 1970s, when the first IC, silicon-based IC came into existence, 1971. Since then, till date, they are pushing to. So this is just a postulate. This is not some kind of a law. So this is kind of an unwritten kind of a drive which the industry and academia across the globe, industry, research institutes and academia across the globe are focusing upon. And they continue to surge forward with this thing in mind. So number of transistors kind of double every 18 or 24 months. And Moore's law predicts that this trend will continue into the foreseeable future. So even now, if you see, it is 11 nanometer or 10 nanometer trying for 7 nanometer, going to 5, then 3, then 2, then 1. So up to 2030, everything is focused on scaling down and how to achieve this scaling down of transistor without any ill effects. Now before we move how to scale down the transistor,
అయినా దాన్ని చెరిపేటి కెరటాలు పుట్టలేదు తెలుసా ఆ గోరువంక పక్కన రామచిలుక ఎంత చక్కనా అంతకంటే చక్కనంట నువ్వుంటే నా పక్కన అప్పుడే విన్నానే కొత్త కొత్త మాటలని
We need to know.
తప్పకుండా
Hello,
విన్నానే
are you
భూమి
still there?
పైన భాషలన్నీ
Yes, sir.
Yeah. So they are
చెప్పలేమన్నా
the
ఏ
three
అక్షరాలు
parameters
ప్రేమని
which are the guiding
కన్నీలి
principle for scaling
సముద్రం
down are
మనసేమో
the length,
అందుట్లో
the
పడవ
width, and the
ప్రయాణం
oxide thickness. So we will be talking somewhat in detail about
నీలో
how to
ముత్యాల హారం
effectively
నన్ను తీరానికి లాగేటి దారం దారం
achieve this postulate, which helps us to double the number of transistor every 18 or 24 months. But before that, we also need to see some of the other important parameters, which is what I had talked before, that our MOSFET transistor is not essentially a 3-terminal device but a 4-terminal device. So that 4-terminal happens to be the body. So we talked about source, drain, and gate terminals. But we generally did not talk, or we said, okay, we are just grounding the 4-terminal, which is the body terminal. But if we apply a particular voltage or a bias on this 4th terminal, what happens? So what we have is the so-called body effect. So what happens if the body is applied by this kind of voltage? So to keep the source and drain junctions remain in the reverse bias condition, we apply the body voltage less than 0, which is basically negative. So this decreases the impact of the gate bias and hence increase the threshold voltage. So I did ask you what all different methods can be used to change or manipulate the threshold voltage. So this is, if you were knowing before in detail, then you must have written in the exam. Otherwise, please note it down. So if you apply a particular bias on the body, it will surely change the threshold voltage, and since it changes the threshold voltage, we say that we can take charge and manipulate the threshold voltage. So gamma is equal to 2 theta q n sub by C of where n is the doping concentration of the substrate and gamma is the body coefficient, while VSB is the source body potential. Okay, class.
Yes, sir.
I think you have a class now, no? T310 or something like that.
Yes, sir.
Okay, so we will start from here. Can I continue for another 8 minutes. What would you propose? I think let's call it off, and then maybe this coming Friday we will continue from where we left. Is that fine?
Yes, sir.
Okay, thank you.
Thank you, sir.